All right, so I think we will pick up today where we left off last time with the first derivative test. And what this is designed to do is help us identify whether a relative extreme point is a maximum or a minimum. Okay, we know how to find the extrema by taking the first derivative of a function and setting it equal to 0. And that's because if you look at these graphs, you'll notice that whether a point is a maximum or a minimum, the one thing they have in common is that the tangent line at that point is equal or has a slope of 0. Okay, it's flat. The problem with that, though, is that it doesn't tell us whether each of these extreme points is a maximum or a minimum. That's just the first derivative by itself isn't enough to tell us that. So what do we do to figure out whether these points we've identified are maxima or minima? Well, the first derivative test tells us that if we have a relative maximum, then the slope of this curve, or the first derivative of the tangent line, slope of the tangent line, which is the first derivative, should go from positive to 0 to negative, as you can see in this graph. So here is our x star, which is our critical value. And so at that point, the function has a first derivative of 0. The tangent line is flat. Just to the left of it, that slope is positive, and just to the right of it, the slope is negative. So we're going from a first derivative of positive to 0 to negative. On the right-hand side, with the relative minimum, we're doing the opposite. Okay, so notice the slope at exactly x star is equal to 0. The slope to the left of it is negative. The slope to the right of it is positive. So it's that pattern that we're looking for. The pattern of the first derivative near the extreme points is what's giving it away. It's telling us whether or not this is a maximum or a minimum. All right, so let's look at a specific example. F of x equals x cubed minus 3x squared minus 9x minus 1. So this is a cubic function. And chances are it'll have at least one relative maximum and relative minimum, although there's no guarantee of that. So this is what it looks like. And you can see, yes, there is a maximum and a minimum. The question is, where are they located, and how do we prove whether they're each point is a maximum or a minimum? Imagine we didn't have access to this graph. What would we do? Well, all right, so here's the function. So the first thing we do is take the first derivative, set it equal to 0, to identify the so-called critical points. And so we do that by setting the first derivative equal to 0, because that means that we're looking for the points of x where the tangent line is flat. All right, now in this particular case, we can simplify this a little by dividing both sides by 3. And the reason why this might be helpful is because we can now factor this very easily and quickly and solve for the two solutions of this quadratic equation. So if you were to factor this, you would see that you actually have x minus 3 and x plus 1. By the way, how do you know that? Because remember, these two values that we've chosen, negative 3 and 1, have to have two properties. Their product must equal the constant in this quadratic expression and their sum is the coefficient of x. Okay, so in other words, for a function ax squared plus bx plus c, the two values that we choose when we factor, let's call them m and n, their product is the c term, their sum is the b term. So we chose those two, and you can double check this with FOIL if you need to. We set them equal to 0, and since their product equals 0, what we actually need is to find out where each one individually equals 0. So we set them both equal to 0 and solve for x. So these 2 points that we just identified are called critical values. And those are candidate points that could potentially at least be maxima or minima. They don't have to be, but they could be. And so what we're going to do now is try to figure out which they are. So how do we do that? Well, what we are looking for is the pattern of how the first derivative behaves in the neighborhood of these 2 points. So let's say, for example, for -1. All right, we already know that this is a critical value. It might be a maximum and it might be a minimum. Well, the slope of the tangent line at that point is equal to 0, as we know. Let's try a value of x that's slightly to the left of that, and let's say -1.1. Plugging that into the function, or the derivative, I should say, f prime of x, as you remember, equals here it is, 3x squared minus 6x minus 9. So if I want to evaluate this, let's say f prime of -1.1. So we don't need the exact value, we just need the sign. So -1.1 squared times 3 I have 1.23. So that's definitely positive. And then if we go slightly to the right, let's say, for example, -0.9. And that's -6.03, which is negative. So this is the pattern that we're seeing here in this graph. Right here, we have a slope of 0. Just to the left of that, we have a positive slope. And just to the right of that, we have a negative slope. And that tells us that this is a maximum. Now, we don't know just yet if it's a relative maximum or a global maximum, but we do know that it's a maximum. And then we also have the critical value of +3 to consider. So here you can see exactly how that works. So I've already gone ahead and done this. You can see that f prime of 2.9 is negative. F prime of 3.1 is positive. So the pattern is exactly what we'd expect for a minimum. It goes from negative to 0 to positive. So what we've been able to do is first identify the critical values, which potentially could be maxima or minima. And then we were able to figure out which one is a maximum and which one is a minimum, simply by looking at the slopes in the immediate neighborhood of that point, 3 and -3 in this case, a -1. So that is our first derivative test. Now here's the final result. I mean, here's the 2 points that we found. Now remember, the original function was way back here, we had the original function. It was x cubed minus 3x squared oh man, and there it is, minus 9x minus 1. Okay, so if you plugged in f of -1, you would discover that it's equal to 4. That's where this comes from. So this ordered pair -1, 4, we call it a critical point. The -1 is called a critical value. That's the value of x at which the function either reaches a maximum or a minimum. And then we do the same thing down here for 3. It turns out that f of 3 is 28, -28 rather. And so this is relative minimum. You can tell by looking at the slopes on either side of that point. All right, now, what we're going to be doing now here is taking a look at the second derivative. So I just want to quickly remind you that the second derivative of a function f double prime of x is the rate of change of the first derivative, f prime of x. Okay, just like the first derivative is the rate of change of the function as x changes, due to given changes in x, let's say. Okay, so it's understood that x is changing, and the first derivative tells us how much the function itself is changing, f of x. The second derivative tells us how much the derivative is changing, or how much the slope of that tangent line is changing as x increases. So we're going to get a lot of useful information from the second derivative. Now, we've got a very important chart here. And so what you're supposed to notice here is, actually, it's getting very cluttered here. Let me draw in a few new graphs here. Suppose we have something like this. What you notice is that the first derivative is positive throughout, but what's happening is that as x increases, the slope is getting steeper, which so that in other words, f prime of x is also increasing. And that means that the second derivative is positive. Aha. Now that's this is where the second derivative becomes so important. The second derivative is positive because the first derivative, as x increases, is getting larger or steeper. Now, here's a case that may surprise you. So the first derivative is negative throughout this entire function. But look what's happening. As x increases, f prime of x becomes less negative. Which means that it's increasing. Oh boy. So in other words, it seems hard to believe, but in both cases, the second derivative is positive. There's a special name for this. When the second derivative is increasing throughout or positive throughout, we call these two cases, they're described as concave up. So what other cases are there? Well, let's try these two. So you can see what's happening here. The slope is positive throughout. But as x increases, the slope is shrinking because the curve is getting flatter. It's not becoming negative, but it's becoming less positive. So that means f prime of x is decreasing as x increases, and that implies in turn that the second derivative is negative. All right, and then there's one more case to consider. How about this one? So the important detail here is that this slope is always negative. But guess what? Oh, yeah, that's right. It's becoming more negative as x increases. That means the slope is getting smaller, more negative. And so once again, the second derivative is negative. Okay. And this case is referred to kind of informally as concave down. So in other words, in these cases, we're not so much interested in the actual sign of the first derivative, but its behavior as x increases. Is it getting bigger? Is it getting smaller? Okay, if it's getting smaller, the second derivative is negative. That's concave down. If the first derivative is increasing, then the second derivative is positive, and we have what's called concave up. All right. So those are the four cases we might encounter. Now, by the way, it turns out that the concept of concavity can also be expressed with geometry. Let me just quickly show you how that works. The two cases here are now reproduced here. And what I've done is I've drawn a secant line through the function in both cases. And the key here is that the secant line is everywhere, in that interval at least, everywhere above the function. And so that is enough to prove that the second derivative is positive, which implies that this is a concave up situation. And by the way, I just want to mention too that sometimes concave up is referred to as convex. But here we'll stick with this notation or terminology, concave up. Now, the last two, these two, when I drew a secant line through these two, you'll see this time the secant line is always below the curve. And that means the second derivative is negative, and these are considered to be concave down. All right. Now, we're going to use not geometry, but calculus to test for concavity with any function that we may have. So first of all, we have to assume that in all these cases, there does in fact exist a second derivative. Otherwise, none of this means anything. So as we've seen already, a second derivative that's positive means that the function is concave up, at least in that interval. And second derivative being negative means it's concave down. All right, now we're going to introduce a very interesting concept. This is something we haven't seen before. It's called an inflection point. And what this refers to is, and by the way, the reason why this matters is because, again, if you look here, concave up and concave down only apply within a given interval. It's not the case that the entire function is concave up and down, or it could be, but it doesn't have to be. So what we're going to do here is claim that within the same function, there could be regions where the function is concave up and regions where it's concave down. So any point where the concavity changes from up to down or down to up will now be defined as an inflection point. So it doesn't matter which way it goes, from up to down or down to up, it still constitutes an inflection point. So let me show you a graph where this is actually happening. Oh, now look at this curve. Now you can see on the left-hand side of that line, the curve is clearly concave up. How can you tell? Because the slope is going from very negative to 0 to very positive. In other words, the slope is increasing. And that implies that the second derivative is positive. But once we get past a certain point, it's the other way around. Look at this. You've got a slope that's going from positive to 0 to negative. The slope is decreasing, which implies a negative second derivative or concave down. At this point A, the second derivative is exactly equal to 0. So it changes from positive to 0 to negative. So this point is known as an inflection point. Now the question is, how do we find it? If it exists, like I said, for many functions, there may not be an inflection point. What we're going to do very simply is take the second derivative of our function and set it equal to 0. Okay. All right, so here's an example. F of x equals x cubed minus 6x squared plus 9x plus 30. Oh, by the way, I sketched in this little graph here. Here's a case where there's no inflection point. This is an upward-facing parabola. And you can see that the slope goes from negative to 0 to positive, which means that for the entire function, the second derivative is positive. So it'll never switch to negative, which implies that there's no inflection point. So in other words, this is an example of a case where there isn't one. Like I said, there doesn't have to be an inflection point. But if it does exist, this is how we're going to find it. So here's what that function looks like, by the way. Yeah, it's getting a little cramped here. Let me do something here. I'll start with a clean copy of it. Okay, that's good. So what are we looking at here? All right, well, the function itself is this. Oops. Just as reference, let me put this here. All right, so the way it's drawn, I mean, it should be pretty clear. Well, maybe it's not clear. We do have a relative maximum and a relative minimum. So we know how to find these. Let's just quickly run through this, just for the practice. So we know that there's two critical values. So we'll find f prime of x, 3x squared minus 12x plus 9. Set that equal to 0. We can divide out both sides by 3. We can factor. Oh, I forgot to divide out. This should be a 3. Now, how do we know that we've done this correctly? If this is m and n, their product has to equal 3, and their sum has to equal to -4. So is that true for -3 and -1? Yes. Okay. So now that means we have x minus 3 equals 0, x equals 3, x equals 1. All right, so let's look at the graph again. So those are the 2 points that could potentially be, well, we can see from the graph, one is a maximum and one is a minimum. So we can use the first derivative test to figure out which is which, but in this case, our primary focus is in finding out if there's a point of inflection here, and if there's any areas where the function is concave up or concave down. So what we're going to do is this. Let's take the second derivative and set it equal to 0. So f prime of x is 3x squared minus 12x plus 9. F double prime of x is 6x minus 12. We set that equal to 0. Aha, 2. All right. Now, if we want to know the exact the y coordinate, we can plug it in here. All right. So let's see. 32. So the point 2 comma 32 is our point of inflection. Right about here. Now, if we want to know where the function is concave up and down, well, you can see for yourselves. I mean, it's clearly concave down on this side. And then concave up here, but let's just prove it. What we're going to do is take the second derivative at a point to the left of 2 and to the right of 2. Okay. So second derivative is 6x minus 12. No, not a good graph. So let's check this out. Let's try f double prime of 1. less than 0. Remember earlier we defined that as concave down. Okay, so negative second derivative means concave down. And now to the right of that point, the inflection point, why don't we just choose 3? That's positive, so that's concave up. So what we were able to determine is that we found our inflection point at x equals 2. And then everywhere to the left of that, the function is concave down, and everywhere to the right of that, it's concave up. Okay. So that's all we needed to do. Now, this leads us up to the so-called second derivative test. Now, this is an alternative to the first derivative test for identifying whether each critical value is a maximum or minimum point. Okay. So again, remember how that works. So the pattern again is f prime of x, if it goes from positive to 0 to negative, that's a maximum. If it goes from negative to 0 to positive, that's a minimum. But that's how we find out whether or not we have each critical point is a minimum or maximum. But we don't have to do this if instead we apply the second derivative test. What we're going to do is this. Whenever we find a critical point C, and by the way, before we tell you the whole thing, let me just see if we can reason this out. Let's say this is our inflection point. You notice that in the first case, where we have a maximum here, we know that the first derivative goes from positive to 0 to negative. But what you also may have noticed here is that within this entire interval, the function is concave down, which is the same thing as saying second derivative is negative. And over here, where we have a minimum, within this interval, the function is concave up, or second derivative is positive. So here's the bottom line. When we find these critical points that might be maxima or minima, we can use the first derivative test to figure out which is which. But here's the alternative. The second derivative test works like this. Wherever the critical point is, if the second derivative is positive, that means that this must be a minimum, because that means the function is concave up. If the function is negative at that point, second derivative is negative at that point, it must be a local maximum, because you can see here the function is concave down. Now, the unfortunate thing about this test, though, is that there can be cases where there is no correct solution. In other words, if we get a 0 here, then we have to try something different. You can't run into that with the first derivative test. Okay, here we have this inconclusive result, which means we have to try something different. But if not, we can just use this instead of the first derivative test, as long as we don't run into this third case. All right, so with all that being said, let's take a look at an example of this. So here's our function. F of x is x to the fifth minus 5x cubed. So we're going to find all local extrema. All right, by the way, here's what the graph looks like. You can see, yeah, it has a relative maximum and a relative minimum, but we have this weird point here. And we knew that this could happen. The tangent line is flat, and yet it's neither a maximum nor a minimum. So keep an eye on that. So here's what we're going to do. We're going to take the first and second derivatives, and we'll find the critical values by setting our first derivative equal to 0. All right, just like we always do. Nothing's changed. Okay. So f prime of x is 5x to the fourth minus 15x squared. And so set that equal to 0. Now, since it's such a high order function, we're going to have multiple solutions. We've got 5x squared times x squared minus 3 equals 0, which implies so we have x equals 0. Over here, we have x squared equals 3. So we've got the three critical points or values. So we're going to check them all out. Okay, now we're not going to use the first derivative test. We're going to use the second derivative test. They can tell from this graph which one is going to be the problematic one, 0. The radical 3 and negative radical 3 are pretty obvious which one they are. So what we're going to do is take these 3 points and take the second derivative and evaluate it at those points. So the first one for 0. The second derivative is 0, which means the test is inconclusive. And you can see why. This is not a maximum or a minimum. What about the other two? Let's try this with negative radical 3. So we plug this into the second derivative. It's negative. Therefore, this is a relative maximum. And you can see that that, of course, is correct. And then we'll do the same thing with positive radical 3. Plug that into the second derivative. It's positive, and that implies a relative minimum. So I put all these together in a nice little chart. And so you can see there's 3 points that could all potentially be maxima or minima. Only 2 of them are, though. We have a relative maximum, we have a relative minimum, and a point that is neither. All right, so that is our second derivative test. Think of it as an alternative approach to the first derivative test to identify whether these critical points are maxima or minima. All right. So that was section 4B. What we're going to do now is move into C. And we're going to be introduced to something really interesting. We're going to be introduced to something called L'Hopital's rule. And what this does is it enables us to take limits for rational functions, in other words, the ratio of 2 functions, where direct substitution of that A gives us 0 over 0. That's known as the indeterminate case. Now, by the way, there's more than one of these indeterminate forms. You can have something like 0 over infinity, or infinity over 0, or infinity over infinity. They're all going to be treated differently. What L'Hopital is saying to us is this. If this is the result of direct substitution. You can still find your limit by doing the following. All you have to do is take the derivative of the numerator and the denominator, and you should be able to find your limit. Okay? Well, that's interesting. So let's try one of these. By the way, keep in mind, this is an important result, a very important result. It'll save us a lot of grief. You'll see down the road. Anyway, so let's take a look at an example of this. What is the limit of the, as x goes to 0, 1 minus cosine x over x? Now, it turns out the cosine of 0 is 1. So direct substitution leaves us with 0 over 0. So that's a problem. And this is what the function looks like. And so how do we find the limit at that point? Well, we're going to do L'Hopital's rule. So the derivative, this limit could be rewritten as the limit of the derivative of 1 minus cosine x over the derivative of x. And of course, don't forget, okay, derivative of cosine x is negative sine x. So here we have 1 minus cosine x. So what we're going to end up with here is, this is actually going to be 0 minus sine x, or just sine x. The denominator is just 1, of course. Oops. But the sine of 0 is just 0. So instead of 0 over 0, we actually end up with a valid result, which is 0. By the way, you can tell by looking at this graph. You remember that we can have limits where there's a hole in the graph, which there is here. But because the limit, as x approaches from the left and from the right, is the same, that means that the limit exists. And in this case, it's equal to 0. All right. Let's try it now. Oh my God, look at this one. E to the 1 over x minus 1 over 1 over x. I shudder to think about what this one must look like. By the way, what would happen if you take the limit of 1 over x? What this means is that x is becoming increasingly large and approaching infinity. Anything divided by that will have a limit of 0. But if that's the case, then here e to the 1 over x will be e to the 0. So this is 0. So once again, we're in one of these strange situations where, fortunately for us, L'Hopital's rule is available to help us out. By the way, this is what the graph looks like. You see there's a couple of asymptotes there. There's an asymptote at x equals 1, and there's a vertical asymptote at y equals 0. X equals 0, sorry. Y equals 1, x equals 0. So here's what we're going to do. We're going to take the derivatives. And if you recall, based on the chain rule, so here g of x is 1 over x. which means that g prime of x is negative x to the minus 2 or negative 1 over x squared. It's in the power rule. And so we're going to have yes, there it is. So the numerator has a derivative of e to the 1 over x times negative x to the minus 2, or we can simply rewrite this as e to the 1 over x, a negative e of, to the 1 over x squared. The denominator of this thing, the derivative of 1 over x is, as I saw set up here, is negative 1 over x squared. So when the dust settles, we're going to end up with, if you directly substitute this limit here, you get e to the 0, which is just 1. Now, as it turns out, L'Hopital's rule also applies when we end up with an indeterminate form, infinity over infinity. Now, like I said, there's different kinds of indeterminate forms. So you should never assume that this is always true. But we know for a fact that it works with 0 over 0 and infinity over infinity cases. How about this one? So again, if you substitute in infinity here, you're just going to wind up with infinity over infinity. Okay, 3 infinity plus 5 is infinity, 2 times infinity plus 1 is infinity. Oh, look at that thing. So let's try L'Hopital's rule. Let's take the derivative of the numerator and the denominator before we apply the limit. Well, this one is very straightforward because you're just going to wind up with the limit as x goes to infinity of 3 over 2. And that's just 3 over 2. The limit of a constant is just equal to the constant, no matter what the limit is heading towards. That was one of the first rules that we learned when we looked at limits. So it makes a big difference between infinity over infinity versus 3 halves. And again, you might be able to see it by looking at this graph. No, maybe not, but it is 3 halves. All right, now here's a wacky one. Oh boy. And again, you can see if I try to replace those x's with infinities, I'll just end up with infinity over infinity. So we have to try L'Hopital's rule, and this is what the function actually looks like, by the way. So we'll do that right now. We'll take the limit, so we'll end up with 1 over x over 5. Actually, it's the limit of 1 over x over 5. Now, when you have your x in the denominator like that, that means that I end up with 0. Okay, notice the denominator, as the limit of x goes to infinity, the denominator is becoming extremely large, so that ratio is converging to 0. Okay. Now, as I mentioned before, there's others. Let's take a look at some of the others. Indeterminate forms, that is. Man, look at some of these. You've got 0 times infinity, infinity minus infinity, infinity raised to the 0 power, 0 raised to the 0 power. These are all pretty terrifying looking values. So the strategy here is if this is what you end up with, you may be able to algebraically rearrange the problem to get it into the form of 0 over 0 or infinity over infinity. And if that's the case, then you can go ahead and use L'Hopital's rule. If not, then you'll have to try something different. Okay, so the only things that work are directly with L'Hopital are 0/0 and infinity/infinity. Now, like, here's a good example. 0 times infinity. We have a limit. X goes to a of f of x times g of x. Suppose it turns out that the limit of x as x approaches a of f of x is 0. And for g of x, that would be infinity. Well, that's going to give us this case. Not what we're looking for. We can't evaluate directly, and we also can't use L'Hopital's rule. So let's look at a case like this. So if we take this limit, yeah, you can see what's going to happen. This is going to go to infinity. This will go to 0. By the way, this is what this graph looks like. What a disaster that is. Yeah, that's a bizarre function. Now, by the way, just as a quick reminder, the limit of x as x goes to infinity, of 1 over x to the n as x goes to infinity is 0, as the limit as x of x to the n power is infinity. So here's the strategy. First of all, let's rewrite this as a ratio. Now we're going to do something unexpected. And you're probably going to say, why? Let's see what we can do about reducing these exponents. Now that's kind of strange. How does that help us? Oh, and by the way, so now what we actually end up with is this, the limit as x goes to infinity. And of course, you know from the rules of the properties of limits, you could, in principle, move this 3 outside. But guess what? This is helping us because the limit now can be solved directly. We have 1 over 1 plus 0. Because as we saw a minute ago, the limit as x goes to infinity of 1 over x squared is just 0. So we actually end up with 3. Ooh, now that was interesting. So anyway, here it is again, formally typed up. So the strategy was to divide everything by the highest order or the highest degree that we find in the equation. In this case, x squared. Because you want this term. This is something we can evaluate. As we saw before, because x squared is getting huge, 1 is staying the same, that ratio is converging to 0. So you can see this is more convenient than what we started out with, where we just wound up with the mess. The strategy, again, was to divide out all the terms by the highest exponent of x. Huh. Now, here's a similar but not identical one. This one's a little different. Now, if you plug in or you evaluate it directly, oh, well, there you go. It's already, that is the correct answer. But if you divide it out by the x, you can see that it's not quite as helpful because we're just going to wind up with infinity over 1 plus 0, but we still will get our answer at least. Okay, now here's another one. This time the exponent in the denominator is the highest. So let's divide everything by x cubed. And of course, only after noting that this is infinity over infinity. So we divide through by that x cubed. We'll end up with 3 times the limit as x goes to infinity, 1 over x over 1 plus 1 over x cubed. So we've got 0 and 0. We got 3 times 0 over 1, which is just 0. All right. So we got a few more cases here, but I think we can stop right here. What comes after this is a couple more examples, and then we'll look at D. Now, this is sort of a preview of what's coming up in the last 2 chapters. These are known as either antiderivatives or integrals, where what you're essentially doing is reversing the process of taking a derivative. So it's a new set of rules that we have to learn, but this is awfully, awfully important. So we'll save this for next time, okay? So I'll see you soon.